Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today I'm going to finish what we started on transactions, which you might remember is what happens when multiple people query the database at the same time, but things can actually happen. As a reminder, this is why it can happen, is that typically the database is behind a website. Website that might be selling things or booking seats in a plane or a banking website and so on. And you might have millions of people using that at the same time. And it means that the database, it's not like it's receiving a query every 10 minutes. It's like it's receiving thousands of queries every second, maybe even more. So you have to really imagine that it's the throughput and the number of queries per second is very high. In fact, one of the performance metrics that we use for saying how good a database system is not so much how much time it takes for a query. That's the problem of the user. It's how many queries it's able to process per second, queries per second, QPS. And of course, when you have millions of people doing it at the same time, a lot of things can go wrong. And there are two typical use cases that are given. One is people are booking seats on a plane and two people are given the same seats at the same time, just because there was an issue with the transactions at the same time. Another example is that when you want to do wire transfers between banks, you have to make sure that you don't credit on one side without debiting on the other side, or even worse, debiting on one side without crediting on the other side. This problem can be actually solved to a large extent with existing systems. That is actually yet one more benefit of using a relational database management system instead of Python, because trying to solve that in Python would I think, literally cost millions of dollars, because this is the kind of person hours that have been put into a system like PostgreSQL or others. And you get that just out of the box and free, because there's a lot of free relational database management systems out there. And so in order to explain the sort of things that can happen and how to mitigate that and prevent this from happening, we have a bit of a theory. As Bowen was saying, for computer scientists, they spend several weeks over that. It's actually very complex, but I'm not going to go into all of these details. I'm just keeping it on the high level, just so that you understand what's going on, and so that you understand what typically you can write in SQL as a user to solve that. So the theory is based on what's called a schedule, which is just a list of small queries, a select, an update, an insert, like these small queries, like one statement at a time. And for every small query like this, we are interested in two things. The first thing is who is executing that query. Who meaning which transaction. Can be Alice, Bob, we can give them names because it makes it easier, but basically these are transactions. So every query belongs to a transaction. For example, what's on the left here belongs to Alice, and what's on the right belongs to Bob, right? So these are the transactions by Alice, these are the transactions by Bob. And that I write typically as a subscript here, right here, to say which one it is. The second thing we're interested in is what that query is about. And this one reads Albert Einstein. This one reads Albert Einstein. This one writes to Albert Einstein. This one writes to Albert Einstein. Then we read to Albert Einstein, and then we read to Albert Einstein. So this is why we abstract away with an R or a W for read or write, the name of which transaction it is, Alice, Bob, and so on, and then the data that is being read. In that case, it's all Albert Einstein. In other cases, it can be multiple places, and we call them alpha, beta. There's plenty of notations. What is important is that there is a specific order in that schedule, and that is just some hypothetical order in which the queries are actually executed in real life, right? So in real life, time elapses top down like this, and we go like this, then this, then this, then this, then this, then this, which is exactly that list right here. Who understands how this maps to this, right? Because this is just a shorthand representation on one line, and this is just the graphical representation of the same thing, even with query details. Who understands the mapping between the two? Okay, very good. So normally, if I give you this, you should be able to produce that without, of course, the actual queries, but you should be able to produce the graph like that. Okay. And so what we do, once we convert this to this representation, we add these little rows here that represent all of the conflicts. Here we have a read-write conflict. Here we have a write-write conflict. And here we have a write-read conflict. Read-read conflicts, that doesn't exist. You don't care if multiple people read. It doesn't matter in what order they read. But all of these rows basically say that the order is important. Now, I give you a more formal example as an exercise last week that who looked into this one? Okay, then let's do it together. Okay. So this is a schedule. It's like we have Albert, Bob, and Carol, who are all reading and writing to and from the database. How many records are they touching? How many values? Alpha and beta, right? So that's two of them. And of course, whenever we look at the conflicts, it's only from alpha to alpha and from beta to beta, right? Because alpha and beta are two different places in the database, so they don't interfere. So the first thing I'm going to do is to display this as some form of table like this. And I'm just following exactly the same order, left to right, but in the table, I'm doing it top down, right? So the first row corresponds to the first on the left. So this is the first row right here, the second row right here, the third row right here, the fourth row, and just left to right is the same as top down. But every time I'm going to pay attention to the subscript right here, and I'm going to put it in the right column depending on the subscript. So all the A's, A, they are in column A, all the B's, they are in column B, and the C's, they are in column C, right? So on every row, I only have it in one column. This is just in order to display. It's not a relation, I mean, it is, of course, a relational table, but we don't actually view this as a relational table. This is just a graphical representation of the schedule, right? Now I have this basically would be the equivalent of this, but without the row, right? In that case, there's 2 columns and 6 rows, but here I just put it in a more structured way. And what we need to do now is to try to add these rows between the small queries to identify the read-write conflicts, the write-read conflicts, and the write-write conflicts. So who can give me examples of conflicts, like where should I put my arrows, right? Yes, go ahead. So let me, it's from here to here, right? Yeah. This one?
The other, in the column C.
Column C, yeah, this? Yeah, this one.
Yeah.
Exactly, there's an arrow from here to here. It's both alpha, that's why it's a conflict, and it's right conflict. So there is an arrow from here to here. There's another one from here to here, and there's another one from here to here. Any other arrows that I could add? Again, it has to be both alpha or both beta, and one of them has to be a read. Yes, go ahead. Yes, absolutely. These two are beta, and this is a right conflict. Any others? There are plenty of them. Try to find them. Yes, go ahead. Yeah, absolutely. You see, it's alpha and alpha, so this is the same place, and we have a read-write conflict between A and B, absolutely. Another one? It is a read-read conflict that wouldn't be a conflict, but here is read-write. The reason we are putting the arrow is that if you would switch the order between the two, and first write and then read, that would change the read. Right? Because then you would read whatever B has written here. A would see what B has written. So the order in which these two are executed is actually important. Does it make sense? If
Yes, but like on the other hand, the reading, because you want to see what's
Yes, but Alice is seeing what was written before, right? So there was some value before. And if Alice reads first, then she's going to see the value that existed before. And after that, Bob, is going to write a new value visible to the future. What we care about is if we swapped the order. So if we swapped the order here, what would happen is that Alice would no longer see the value from the past, but she would see the value by Bob, right? And what we're saying, it's not that it's wrong. Maybe that also makes sense, but it's different. This is just something that's happened differently because Alice sees something different. And these little rows, they basically tell us, careful, careful, here the order matters. You cannot just swap them without modifying what's going on, right? That's what we're doing, okay? So let me add you some arrows here. So there's here, there are also here. These are the write-write conflicts in here from W to W. Then we have read-write, 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 and read-write on beta, read-write on alpha. And then we have also read-write here and read-write right there, okay? So we have, and again, write, read, write, read. So you see there are so many of them, right? So this is what we get. We basically get this graph. These rows basically tell us, careful, the order is important. You cannot just swap the order without modifying what's going on. And what we want to see here, we basically want to disentangle spaghetti. It's like eating spaghetti and trying to disentangle it. So basically, Alice, Bob, and Carol, they are just doing their thing at the same time, their transactions. And in the beautiful world in which there are no problems with concurrent transactions, it's basically Alice first, then Bob, and then Carol. Or maybe Carol first, and then Bob, and then Alice, but basically in that order. And here it's all entangled. There is no order between Alice, Bob, and Carol, right? How do I see it? I'm basically trying now to forget about the individual queries, but I'm just interested in Alice, Bob, and Carol. What I see here is that there exists an arrow that goes somewhere in Alice's transaction to somewhere in Bob's transaction, from here to here. There is also one from Bob to Carol. Doesn't matter which one you pick, but there exists one. There exists also one that goes from Carol to Alice, right? There exists also one from Bob to Alice. There exists one from Alice to Carol, right? And there exists one from Carol to Bob. In fact, there exists arrows between any combination of Alice, Bob, and Carol in any order, and you can actually abstract it away like this, right? And this graph tells us that it's not possible to reorder these queries in a way that we are going to disentangle the spaghetti. And the reason we can't is that there are cycles. You can basically follow the arrows of that graph, start anywhere, for example, here. And if you follow an arrow, then follow another arrow, then follow another arrow, you're back to where you were. That's called a cycle, right? You basically can cycle this, and in fact, you can also cycle the other way around in that case. The fact that there is a cycle tells us that there's no way we can put an order in Alice, Bob, and Carol, because Bob would have to be before Carol or Charles, it doesn't matter, ABC. Bob would need to be before Carol. Carol would have to be before Alice, and Alice would have to be before Bob. That's not possible. You will not be able to find an order like that. So in that case, we know that we have a problem because there is this spaghetti that we cannot disentangle. If I come back to the conflict we had before, so that was the example I gave you last week, right, with this more formal one. If I come back to the previous one with the Albert Einstein bank account, what you notice here is that there also exists an arrow going from somewhere in the left to somewhere on the right, and there also is an arrow going from somewhere on the right to somewhere in on the left, right? So basically, I also have a cycle here. There is no way I can say it's the first Alice and then Bob, or first Bob and Alice because of that spaghetti right here, right? Okay, now I'm going to show you an example where we can disentangle the spaghetti, right? Because there are cases in which we can. Well, first, the obvious case where we can disentangle the spaghetti is if there is no spaghetti at all. So let me take an example where the ordering of the small queries is such that it's Alice first, all of Alice's queries, query 1, query 2, query 3, all first, and then Bob queries, Bob 1, Bob 2, Bob 3, right? You see that in that case, there is no spaghetti because all of my arrows, they go from the left to the right, right? So I have Alice first, and then I have Bob. So there's no conflict between the two, right? It's nicely serial, and this is what we call a serial schedule. This we love in databases because it means that it's as if all of that was a single big query followed by another single big query by Bob. And that is that brings a lot of joy and happiness to database scientists. Let's put it that way, right? So we don't have any spaghetti. And you see that there are the rows going from the left to the right, but not going from the right to the left. So this is a graph that doesn't have any cycle. And we can actually deduce from that graph that we can put all of Alice's transactions first and then Bob's transactions. Well, in that case, it was already the case, so there's nothing to do. So that's a serial schedule. Now, you can even enforce that to kind of say you want to ideally for things to ideally be that way by adding in your SQL code a begin and a commit. So Alice starts her queries with a begin and then the 3 queries and then a commit at the end. Bob does the same. He starts with a begin, then he issues the 3 queries and then a commit. That is kind of hinting PostgreSQL that we would like to be an order between Alice and Bob, right? So for example, here Alice first and then Bob, right? Why is that useful? Because PostgreSQL can cheat like this. Does it change anything? It doesn't, right? Because what did I swap here? I just started the first query by Bob before the last query by Alice. Why is that not a problem? So it means that Bob reads before Alice reads, and before it was Alice reading before Bob reads. Why is that not a problem? Yes? Exactly. We don't have a problem because Alice has already written. Bob will write later. And what we swapped are 2 reads. So there's no problem swapping reads, right? It doesn't matter in which order they read the data. So this is why PostgreSQL cheats and reorders a little bit. It basically is nice to Bob and letting Bob begin the transactions before Alice is finished. That's more efficient, right? Going to be able to execute more in less time. And it doesn't change the behavior of the system because Alice and Bob, if you tell Alice and Bob, was it like this or like that? They wouldn't be able to tell you. It makes no difference to them, right? So here, basically, we say that the schedule here is serializable. It's not serial because you don't have Alice first, then Bob, but it's serializable because you're able to reorder things in a way that nobody notices. Now you can convert it to a serial schedule like this, disentangling. Okay, and now if you look at this here, the serializable one, the one that is slightly entangled, but you can reorder it, the way you can tell that it is serializable is that, again, there's arrows from the left to the right, but there are no arrows from the right to the left, right? So the graph is the same. This is what tells you that a schedule is serializable. So serializable means there are no cycles in the graph of transactions. This is the graph of transactions. Does that make sense? Right? And so basically, when you have a graph like that, you can basically decide, or PostgreSQL basically sees that it's as if Alice executed everything first and then Bob executed everything. We can reorder in that way. Now, this one, what did I want to say? Yes, exactly. I'm just repeating the same thing. So there is a fancy name for the serial schedule that is equivalent to the serializable one. We call it a conflict equivalent serial schedule. It's a serial schedule that is conflict equivalent to this. Okay? Right. So this is the idea. And so, you know, if I give now that to PostgreSQL, and I would like to execute transactions here, PostgreSQL might try to disentangle things. Maybe let's pretend it doesn't know about the graph of transactions and the cycles. So maybe it's going to try this, right? It's going to say, okay, maybe I can try to swap this and this. Maybe I can swap also these ones and so on. But no matter how you try, because the arrow constrains you, right? The arrows constrain you. You cannot swap the red ones, for example. You cannot swap a red one with a green one. That does not possible. You cannot swap an update with a select. And you're blocked. That's pretty much all you can do here, right? There's not so much you can do. You're stuck. There is no way you can disentangle them. Who sees that? That there is no way here? And basically, we see that because there is a cycle. So the easy way is, again, draw this, and you see the cycle, and then you can say, okay, no matter how hard you try, you're not going to be able to disentangle the spaghetti. There is no way you can nicely reorder Alice and Bob. Okay? Now, I'm not gonna go into the implementation. That's exactly what is several weeks of teaching for computer scientists. I'm just gonna tell you on a very high level, as a user of SQL, how you can type things into your Jupyter notebooks or in C++ or Java or Python when you connect to PostgreSQL. So you already know begin and commit, right? So the idea is that if you are writing to PostgreSQL several queries, and these queries belong together, you would like them to kind of be packaged together. For example, a series of queries might be, what are the occupied seats in the plane? And then please mark that seat now that was not occupied, mark it as occupied for Mr. and Mrs. Smith, and then take the payment and blah, blah, blah. So this is a series of queries. This is the kind of queries you want to group together in a single transaction, with the idea that you don't want that to interfere with other people, right? Because if Mr. and Mrs. Johnson are just going to also book their seats and at the same time, they might both be assigned to the same seats, right? So you don't want that. All right. So the way you do that is you write begin, semicolon, then you write all of your queries, and then you write commit. That's a way of hinting PostgreSQL that these transactions belong together. Now, you might change your minds. You might start a transaction and notice that something's wrong. Maybe something unanticipated happens. For example, there are no available seats or something like that. Or maybe the customer canceled or something. Then what you do, instead of commit, you say rollback. And basically, the idea of rollback is you cancel everything. You ask PostgreSQL, please forget about everything I've done, these 3 queries, please do as if it never happened. So when you roll back, it means that, so the select, of course, you don't care, but the update will be canceled. It is as if it never happened. So after the rollback, normally the balance of Albert Einstein should be back to the old one before it happened. For whom does that make sense? Right? So you start a transaction, and then 2 things can happen. Either you commit, and then everything is applied, or you roll back, and then nothing is applied. It's all or nothing. In some cases, you might be forced to roll back by PostgreSQL. Maybe PostgreSQL will allow you to start a transaction, and then right in the middle of it, it's going to be like, stop, something bad happened, there are too many people, and there's too much spaghetti that I cannot disentangle. Now I'm rolling you back. So you have to start all over again, but I'm rolling you back. So this is a rollback, can either be by the user like this or forced by PostgreSQL. Okay. Now, the one more thing that I want to show you is this transaction isolation level, which is a fancy knob that you can turn with PostgreSQL. If you want to ensure serializability in the sense that it's as if it was you first and then somebody else, like you have this order, all you need to say is begin and then set transaction isolation level serializable. That will guarantee you something like this, right? That's guaranteeing you that this is what's going to happen, and it's guaranteeing you that this will not happen. If that's about to happen, you will get an error or it will be rolled back, but you're guaranteed with this set transaction isolation level serializable, this is never going to happen, right? Does that make sense? So all of this of drawing the arrows and finding out if it's serializable or not, it's a nice exercise. But in practice, when you use PostgreSQL, it's as simple as just writing that. Set transaction isolation level serializable. That's kind of the shield that protects you from the outside world, right? And you know that it's all or nothing, and you know it will not interfere with other people. That's pretty simple, right? It's just 3 lines to add, just like that, and then put your queries in the middle, and it works. Now, there's other isolation levels that I would like to tell you about that are a bit less strict, because if you're too strict, imagine that everybody writes that. Everybody writes transaction isolation level serializable, and all of them have like 1,000 queries in the middle. PostgreSQL is going to go mad. There is no way you can just do something with such a high requirement that everything is serializable with a lot of big transactions. So you have the possibility to kind of be nice to PostgreSQL and be less demanding and say, okay, it's okay if it's not serializable, that's okay, but at least give me some guarantees. And I'm going to tell you what sort of guarantees you can ask if you want to not be as demanding as serializability. So first, I'm going to tell you 4 bad things that could happen in increasing order of, in decreasing order of severity. The worst thing that can happen is what we call a dirty read. A dirty read is when you're a transaction, Alice, and you run your queries, and then you see data that Bob wrote, but it's not even committed. Bob was just running the transaction, it's not even committed. That is what could happen if you're booking your plane seats, and then suddenly the seats that you were able to order and you entered your credit card details and so on, and suddenly it's occupied. And that's because somebody else in the meantime did that. That's a dirty read when that happens. And of course, if you already booked a flight on a train ticket, you notice that it does not happen, right? Once you have blocked it, it stays blocked for a while, and nobody else can take it for a moment, right? So that's a dirty read. That's the worst thing that could happen. Then we have something that could happen that is a bit, it's less severe than a dirty read. So it's a non-repeatable read. So a non-repeatable read, basically, is what happens when you read some data multiple times and it changes. So if you read data, read, and read again, and then it changes, it means, hey, I'm not alone. Somebody else is on the database. So I'm seeing the effects of other people, right? So I'm not well isolated. I find it to be changed. But it's not a dirty read because that data you see changed was committed by somebody else in the meantime, right? So that would be that would not be dirty, because dirty means it's uncommitted. It was somebody who did not even commit, right? And you see the nightmare that it would be to roll that back, because now you've seen it, it's too late. You cannot unsee it, right? So that's a non-repeatable read, right? So non-repeatable read means you're sitting in front of your computer and you're looking at the occupancy of the plane, and you're hitting the button refresh. Then you see that a seat became occupied. It means that somebody paid with their credit card and now they booked the seats. That's a non-repeatable read. Now, if you want to go further, no dirty reads, no non-repeatable read. If you click refresh, you always see the same thing. If you repeat, you can still have what is called a phantom read. It's no longer Halloween, but nevertheless, the idea of a phantom read is that it's not data that would change. It's new data that would pop up out of nowhere. You're sitting in front of your desktop computer booking your plane, and there's a new seat that pops up, right? So this would be a phantom read. It means that you run the queries multiple times, and suddenly you have more rows. 2 or 3 or 4 more rows just appear out of nowhere in your query. Note that the data in the other rows are unchanged, because otherwise it would be non-repeatable. But here it's just that there's extra rows. That's a phantom read, right? And the 4th phenomenon that can happen, and this is the one we've seen, is called a serialization anomaly. It's the idea that you have Alice and Bob executing their transactions, but there's no way that it would be equivalent to a specific order, right? Again, I told you what brings joy and happiness to database people is when you have this nice global order between the transactions, and every transaction goes one after the other. Serialization anomaly means that you were not able to have an equivalent order of transactions. That's a serialization anomaly. And note that, again, this is kind of negligible in many cases. Many people don't care about that, right? This is a bit more bad. This is worse. This is even worse, and this is even worse, right? So this is the idea. And basically, depending on what you're scared about or what you want to avoid for your system, you can specify, that's the line that I showed you here, right? Set transaction isolation level serializable. Well, if you want to be nice to PostgreSQL, you can be less demanding, and instead of require serializability, you would have you would basically lower your expectations and say, okay, I only want a repeatable read or read committed or read uncommitted and so on. So you can basically specify these levels that you want to forbid. And I noticed I made a mistake because serializable would also prevent serialization anomalies. I would change the last tick on the bottom right to a red one. So you basically have all of these levels. Not all databases have them all. So in fact, PostgreSQL technically doesn't support read uncommitted. It will interpret it as a read committed, which is okay because it's more strict, right? So it's not going to be worse. So this is the idea. And what I want to say here is really the idea that you can specify your requirements to PostgreSQL. You can basically tell PostgreSQL what you're afraid of, what you don't want to happen, and then set the knob of your isolation level the way you want. So serializable is like I'm completely isolated from the world. It's as if I were the only human being ever touching the database. And read uncommitted is the worst because you see everything that's happening with other people touching the database, right? So that's the idea. Okay. And so that's an example. If, for example, I changed it to something else that's serializable, I say read committed, and that would just prevent the dirty reads, but I could still have non-repeatable reads, phantom reads, and so on. And the concluding slide here is this ACID. Who heard of ACID? ACID is just an easy way of remembering the 4 guarantees of transactions. A is for atomicity, C is for consistency, I is for isolation, and D is for durability. These are all the nice things that we want in a proper system like PostgreSQL or others that nicely handle transactions. So atomicity is this commit rollback thing. Atomicity means either you commit or you roll back. If you commit, everything will have been executed, all your updates. If you roll back, nothing will have been executed. But atomicity means it cannot be half of it, right? Imagine you execute a transaction and half of that transaction was actually applied and the rest was just dropped. That is not nice, right? Atomicity guarantees it's either everything or nothing within the begin commit block or rollback. Okay, then consistency means that the database is consistent at all times. What it means is, you remember that in the schema of the database with create table, you had this not null or check consistency constraints or unique, or you can add something that something must be positive or a value must be the sum of other values, right? Remember this when we designed the schemas? Who remembers this create table in the constraints? So consistency in the C means between transactions, you have the guarantee that these constraints that you put in your schema hold. In the middle of a transaction, that might temporarily not be the case because you might need to modify 2 values, right, to bring back to consistency. So in the middle of a transaction, you might be temporarily inconsistent, but as long as you're done with the transaction committed or rollback, it must always be consistent between the transactions. That is called consistency. The third one is isolation. That is the serializability thing. Isolation means you're sitting in front of your computer and it's like you're the only customer of the airline on the planet, right? You don't even see anybody else because you're fully isolated. Of course, it's not true. It's only that PostgreSQL is making you believe that, right? Because of the implementation. But it's as if the transactions were executed serially. That's the isolation. That's the one you can turn a knob, like make it less stringent. And durability is your change will not be lost because once you have paid with your credit cards for your seat on a train or any other means of transport. You don't want the seat to go away, right? You want that to persist. And that is called durability. And that must also be the case if the electricity is switched off, if you power off the cluster and power it on again and so on. That's called durability, right? All of your updates are visible in the future until somebody modifies, of course, but at least it should not be lost. This is called ACID. And that's any computer scientist will have heard of that because this is a very common acronym. Again, in a bachelor's lecture for computer scientists, we might go 2 or 3 more weeks explaining all of the details of how PostgreSQL is good at making you believe you're the only user in the world, because it's very complex actually to do. But for you, all you need to know is that you can just put this begin and this commit or this rollback. Again, it's Java or C++, so you can program all that. And you can pick your isolation level in order to say what you don't want to happen. Okay, who is with me? Yes, okay. Any questions? No questions? Okay. So again, if you want to keep in mind the reason for this, think of a bank where you want to make sure that when you debit, you also credit, and think of reserving a train ticket or a hotel room or anything that you don't want for several people to be allocated the same room and so on. That's the idea why we are doing this. Okay. Note that there are chapters in the book, right? I'm always giving you chapters. It's always a good idea to read the book. So every week in the Moodle, you will find the corresponding chapters and sections that explain you. Because maybe the book does a better job than me at explaining you all that, right? Okay, so then I'm going to start. I have a few minutes until the break. I'm going to start with the views and indices. Then, okay, last call for questions. Okay.
Of the voice code overflow, if you don't have a voice code overflow, I just understand it last week.
Mm-hmm. So the normal forms, right? Yeah. Ah, I see. Okay. So let me take the minutes until the break in order to explain that, and then I'll start views and indices after the break. The normal forms are a best practice for designing the schemas of your tables, right? You build a new website, you build a new web shop and so on, and you're thinking, what should my tables look like? All the people who create startups, it's one of the things they have to do at the beginning, right? To design the database schemas. The normal forms, they give you a theory that says this is good, this is bad, right? The rule of thumb is the idea that it's better to have one table for every meaningful kind of things you're manipulating. One table for the products, one table for the orders, one table for the customers, and so on and so on. As opposed to a single big table that has everything. And the reason is that if you do have a single big table that has everything in it, you're going to have a lot of duplication, a lot of redundancy in there, and there's going to be a lot of trouble that's going to happen when your website is running, because then you're going to modify the database. But because of the redundancy, whenever you modify something, you must remember to also modify it somewhere else, and that might actually fail, right? So this is the reason why we consider it to be bad design if you have a single big table with everything, and good design if you nicely split the tables. Now, this is captured formally with the definitions of the normal forms. There are really just 2 normal forms that you have to know, right? The first one, it's just the idea that you don't have a table in a table in a table, right? All your values are always single atomic values. So that's the first normal form, atomic integrity. And the second one that you must know is the Boyce code normal form, just these 2. Second, third, I just told you they existed and that they are kind of in between the first and Boyce code, but you don't need to know the details of that. So it's just Boyce code. Now, the definition of a Boyce code normal form is done on top of functional dependencies, right? And the functional dependencies are a way of saying that if you have specific values in some column, then you must also have some other value in another column, right? If two tuples match on for example, the social security number, then they must also match on the name, right? And based on these functional dependencies that a table may or may not fulfill, some of the functional dependencies are good and some of the functional dependencies are bad. The functional dependencies that we love are the functional dependencies such that what you have on the left of the functional dependency is a super key, right? And a super key means that these are the values that would determine the whole record, right? If you know the values in the super key, you know the whole record. These we love. These are the functional dependencies we love to see. The functional dependencies we don't like to see is if you have a group of attributes implying another group of attributes, but what you have on the left doesn't determine the whole record. It's only partial. And this is going to happen if you have an enormous table with the products, the customers, and so on. An example of that was when I show you the phone, the TV, and the price, and so on. So the ID of the product determines the price. That's not a super key because in the table, you also have the customers and so on. You have so many things that basically it's not a super key. This is bad. And the Boyce code normal form just says, I only want the good ones, the good functional dependencies. I don't want to see any of the bad functional dependencies, right? So that's what the Boyce code normal form is about. Now, what if you do have bad functional dependencies and you have a schema design that is not in Boyce code normal form? How to fix it, right? And in fact, for every normal form, that's also true for the first, for the second, for the third, there's not only a definition of the normal form, but there's also an algorithm that tells you how to fix it. If it's not in normal form, how do you fix it into something that is in the normal form? So we only did it for Boyce code. And I gave you a way when you have a big table that has bad functional dependencies, how do we split it into multiple tables to only have good functional dependencies remaining? And the way you do the decomposition is you pick a bad functional dependency. There might be several, right? But you pick one of the bad dependencies, and you use that dependency to guide how you split. And the idea is that, let's say that we have a set of attributes that I'm calling S, that functionally determines a set of attributes that's implying T. And you compute you try to compute the closure of S to have all of them, right? So you take S together with all of the attributes that depend on S, that gives you the first table on the left, right, of your decomposition. Now, it's a bad functional dependency, so S is not a super key. So it means that you're not going to have all of the attributes. If it were a super key, you would have all of them, right? But S is not a super key. So what you get in the transitive closure of S is only a part of the table. So what you need to do as your second table for the decomposition is also S, because you need S to basically join the two, S plus everything else that you were not able to put in the first table. And that gives you a decomposition, right? Now, what you need to do next, because you might not be done, it might be that this is not enough, that this decomposition is not enough. So you need to take all of your original dependencies, project them to the new tables, and now look again if there are still bad dependencies. And if in one of the two tables, or maybe both of them, there is again a bad dependency, you just go recursively. You use it again, you decompose again, project again, and so on. And you go all the way until there's no bad functional dependency left. Then you have reached a database with multiple tables, and all of them are in the Boyce code normal form. There might be more than one way, because it depends on which bad dependency you're taking. And so in one of the exercise quizzes that I think you were also asking before, we're asking to you which one of these possible decompositions, one of them is actually correct. If you do it that way, this is correct, but all the others are incorrect, and you need to pick the correct one. And in order to determine this, you really need to look at the bad dependencies. What are the bad dependencies that break the Boyce code normal form? And that gives you the hint on how to decompose. Now, you can there's two ways of doing that. Either you look at all of them and try to use the Chase algorithm to see that something's wrong, because if you decompose normally, the Chase algorithm succeeds. And if the Chase algorithm doesn't, it means the decomposition is incorrect. So this is one way of doing it. You can use the Chase algorithm. The other way of doing it is to do the decomposition yourself, right? So you take one of the two dependencies. There's only two in that question, right? So that's rather easy. It's either the first one and then the second one, or the opposites. And so you can just try to do the decomposition, and normally one of the two ways will give you one of the answers. This is the other way you can solve the question. So it's a case where I think you get 3 tables. So it means you have two decompositions to do, right? Did it help? Yeah, awesome. So let's take a break, 15 minutes, and then we'll talk about views and indices.